Steel is the hero of the modern world. We put it in bridges, towers, tunnels, almost everywhere. But there's a quiet enemy that steel can't muscle through: time. If you've ever seen a chunk of concrete flake off a bridge or parking garage, that's often time working through a simple chain reaction. Water sneaks in, salts sneak in, the steel inside starts to rust, and rust expands like a wedge. The concrete cracks, then chips, then the damage spreads. For reinforced concrete, engineers have been saying the same thing for decades. Corrosion of the internal steel is a major driver of deterioration in many structures, especially where chlorides from seawater or de-icing salts can reach the rebar. Now here's the twist. Around the Mediterranean, some Roman seawalls and buildings have faced waves, storms, and earthquakes for nearly 2,000 years, and parts of them are still standing, still hard, still doing their job. That doesn't mean Roman concrete is stronger than steel in every way. Steel still wins in pure tensile strength, pulling forces. Concrete, ancient or modern, is naturally better at compression, squeezing forces. The Roman advantage shows up somewhere else: durability, and the way cracks can stop before they become disasters. One of the most famous examples is the Pantheon in Rome. Rebuilt under Emperor Hadrian in the 2nd century CE, its massive concrete dome is still there today, an ancient roof that keeps doing its job long after most modern buildings would have needed major repairs. For a long time, historians and engineers stared at Roman concrete and argued about the same question: what did they do differently? Everyone agreed the Romans used volcanic ash, pozzolana, mixed with lime and water to make mortar that could harden strongly, even in harsh, wet conditions. But there was an ugly detail in many samples: little bright white bits sprinkled through the gray. For years, some experts assumed those white chunks were just sloppy mixing, leftover lime that didn't dissolve. That assumption mattered because modern concrete is usually mixed to be as uniform as possible. In modern practice, a batch full of unmixed clumps is a sign something went wrong. On January 6, 2023, a team led by materials scientist Admir Mosic at MIT published evidence that those white chunks weren't just mistakes, they were a feature, and they pointed to an almost forgotten process the Romans used on purpose: hot mixing, involving lime clasts. Let's slow down and name the characters in this story. First is lime. Limestone gets heated until it turns into quicklime, a very reactive material. Add water to quicklime and it slakes, reacts, releases heat, and turns into a different form of lime used in mortars. Second is pozzolana, the volcanic ash the Romans prized. The word is linked to the area around Pozzuoli in Italy, where volcanic material was mined. Mixed with lime and water, pozzolana helps form a binder that performs well in wet environments. Ancient writers like Vitruvius described lime and volcanic ash in Roman building practice. But books don't capture everything builders do, especially across centuries. That's why the physical evidence inside the concrete matters so much. And third is the main problem concrete always faces: cracks. Concrete shrinks as it cures. It expands and contracts with temperature, and it's weak in tension, so cracks are not rare, they're normal. Modern concrete tries to manage cracks with steel reinforcement, careful curing, and additives. But the moment a crack becomes a pathway for water and salt, steel corrosion can start, and that's when damage often accelerates. So when Roman concrete lasted so long, the big question became: how did it deal with cracking without modern rebar, without modern chemistry labs, without our building codes? The MIT team's answer was bold but simple. The Romans sometimes didn't start with already slaked lime paste. Instead, they used quicklime directly in the dry mix, along with volcanic ash and other ingredients. When water hit that dry mix, the quicklime reacted. That reaction produces heat. The researchers argued that heat created hot spots and unusual conditions during mixing and early curing. Those hot conditions can do two important things. One, it can speed up setting and curing, which matters when you're trying to build fast in the real world, not in a perfect lab.
Two, they can create and preserve those white lime clasts, small, brittle, reactive chunks that don't fully dissolve at the start. They stayed trapped like tiny reserve batteries of calcium inside the concrete. This flips the old assumption on its head. What looked like bad quality control may have been deliberate engineering. Leave behind reactive pockets that can wake up later. Here's how the self-healing idea works in plain language. When a crack forms, it often travels through the weakest path. In hot mixed Roman-style concrete, that path can run right through a lime clast because clasts can be porous and brittle. Then water enters the crack. When water touches the lime clast, the clast can release calcium-rich material into the tiny crack space. That calcium can react and form new solid minerals, especially calcium carbonate, right inside the crack. In simple terms, the crack gets filled in with new stone-like material. In the lab, the MIT-led team made modern samples inspired by ancient recipes, cracked them on purpose, and ran water through the cracks. They reported that in samples made with the hot mixing method, the cracks sealed within about 2 weeks and water could no longer flow through. A control sample made without quicklime did not heal the same way. That matters because a sealed crack isn't just cosmetic. A sealed crack blocks the highway that water and salt use to move deeper, and those are the same travelers that help corrosion and other damage spread. Roman durability isn't just about city buildings. Along parts of the Italian coast, researchers have studied Roman marine concrete, old harbor breakwaters that sat in seawater for centuries. On July 3, 2017, researchers, including geologist Marie Jackson, reported evidence that Roman seawater concrete can form rare mineral cements over time, including aluminous tobermorite, as seawater interacts with volcanic materials in the mix. That's a slow, real-world upgrade that happens long after the concrete is placed. These marine studies don't replace the lime clast story, they add to it. Roman concrete wasn't one single recipe, it was a family of recipes that could change depending on local materials and what the structure had to survive. If you're thinking, okay, but did Romans really do this, or is it just a modern guess? This is where Pompeii enters the story. In 79 CE, the eruption of Mount Vesuvius buried Pompeii. Tragic for the people who lived there, but for science, it froze ordinary work in place, like a snapshot. On December 9, 2025, researchers, including Nature Communications study, describing an unfinished construction site in Pompeii's Regio 9. They found piles of dry building materials and partially built walls, rare physical evidence that let scientists see the process before water was even added. Their analyses showed that quicklime had been pre-mixed with dry pozzolan before hydration. In other words, they found direct evidence consistent with hot mixing, not just in a lab recreation, but at a real Roman worksite. The paper also describes how hot mixing creates a heat-releasing reaction and supports lime clast formation, and how those clasts can dissolve later and feed mineral growth that helps densify the material and seal pores and cracks. Here's the honest answer, not in a head-to-head strength contest. Steel is still the champion when you need tension strength, when parts of a structure must resist being pulled apart. That's why modern reinforced concrete uses steel. Concrete handles compression, steel handles tension. But beating steel means something else, beating the failure mode that steel introduces. Steel reinforcement can corrode. Corrosion products take up more space than the original steel, pushing outward and cracking the surrounding concrete. This drives cracking and spalling and can shorten service life, especially in salty environments. Roman concrete, in many cases, didn't rely on internal steel, so it avoided that particular trap. And if its cracks could self-seal, it could slow water movement, which slows many kinds of damage. So the Beat Steel headline works best as a durability story, a 2,000-year-old strategy that can sometimes outlast steel-reinforced systems because it can heal small cracks instead of letting them grow. This isn't just a cool history mystery, it's a climate and infrastructure story. Cement and concrete are everywhere, and the cement sector is a significant source of global CO2 emissions. So when concrete fails early, the cost isn't only money and disruption, it's also more cement, more energy, and more emissions to rebuild and repair. Part of cement's footprint comes from the chemistry and heat of making clinker, an energy-intensive process that reaches about 1450 degrees Celsius in manufacturing. That heat demand is one reason cement is hard to decarbonize quickly. If we can make concrete last longer, we don't need to rebuild as often. Fewer repairs and replacements mean less cement demand over time, and that can reduce emissions across a structure's full life. That's why researchers talk about service life like it's a climate tool. A bridge that lasts 100 years instead of 50 isn't just a nicer bridge, it's a different emissions footprint. Roman-inspired ideas won't solve cement emissions alone, but durability is one of the simplest levers we have. Build once, build well, and stop throwing away structures early. Even with exciting lab results in the Pompeii worksite, there are real open questions. First, was hot mixing widespread across the Roman world? The Pompeii evidence shows it was used there, but practices could vary by region, time period, and local materials. Second, self-healing works best for small cracks. A giant structural crack from an earthquake is not going to magically glue itself together. The goal is to stop tiny cracks from becoming big problems. Third, modern concrete has different demands. We build taller, carry heavier loads, and face different chemicals and climate stresses. Any Roman-inspired method has to be tested, standardized, and proven safe at scale. And finally, there's a human lesson here. The Romans weren't trying to win a lab contest. They were trying to make buildings that lasted. The technology was also a mindset. Treat time as a design requirement. So, what did we really rediscover? Not a myth, not a magic rock, and not a concrete that's literally stronger than steel. We rediscovered a process, hot mixing with quicklime that leaves behind lime clasts, tiny reactive pockets that can help seal cracks later. We rediscovered a clue hidden in plain sight. Those white chunks weren't always failures, they were a strategy. And maybe most importantly, we rediscovered a question modern builders don't ask enough. What if the best material isn't the one that's strongest today, but the one that's still strong after decades of weather, water, and stress? Because in the end, the most futuristic building material might not be new at all. It might be a 2,000-year-old idea, finally understood.